So now we're going to calculate the dot product of the F12 and the F13 vector, and we're actually going to determine the angle between these vectors just using what little we've got here. Okay, and once we've done that, we're going to be able to project one vector on the other and see what that means, what the interpretation of the projection might be. So, just to begin, we know the components of these vectors. Right here they are. So that the dot product is this dotted with this. And got a dot here, a negative sign here. Things got a little bunched up at the end. In any case, the 8 newtons I multiplied by the negative 4.3 newtons times I is going to give us, well, the negative of 8 newtons times 4.3 newtons times I dotted with I dotted with I being 1, we get this. This with this is going to result in an I dot j, so it's going to be 0. This term with this term is going to be a j dot I term, that's going to be 0. And this with this is going to be a j dot j, so we're going to have the 8.9 newtons times the 6.1 newtons. Now you can just, automatically do this times this times this, and that's okay when you're in a big hurry. But if you're not reminding yourself periodically of exactly how this follows from the simple definition of the dot product that I used here, you should be doing that. Okay, well, when we add these up, I think we get something approximately equal to 21 newtons squared, because newtons times newtons is newtons squared. And the magnitudes of these vectors, of course, we've been using these all along, but they can be calculated from the components in the usual manner, and we will come out with 12 newtons and 7.5 newtons, at least rounded to the nearest tenth of a newton. Okay, so since now, using this fact that the dot product is the product of the magnitudes times the cosine of the angle between them, we're going to be able to calculate this angle because we know the dot product, we know this magnitude, we know this magnitude. It's going to be very easy to solve this equation for cosine theta. Doing so, we get cosine theta is this divided by this, here divided by here. And that doesn't require any explanation. We just now substitute F1 dot F2, 21 newtons squared. Magnitudes are 12 newtons and 7.5 newtons. These multiply out to 90. 21 over 90 is approximately 0.23. And from that, we can get that theta should be approximately equal to the inverse cosine of 0.23. Now, earlier we determined that this angle of this vector with respect to the positive x-axis was 48 degrees, and this angle was 125. Okay, the difference between those is 77 degrees, so this inverse cosine ought to come out pretty close to 77 degrees, although it might not come out exactly equal to 77 degrees. So is this equal to 77 degrees? Remember, our 48 degrees and our 125 degrees were rounded off, so there could be a discrepancy because of that. And this is actually, if you want to go into it, 0.23 repeating. I've just rounded it off to 2 significant figures. That could make a difference of a degree or so. Well, let's figure out what it is and see if we're consistent with our preceding results. Well, I went to Excel. Not a good program to use for mathematics, but it's all I happen to have available at this moment. And I got 82 degrees here. Then I realized I transposed my 1 and 2. If I'd used 21, it did come out 77.3 degrees, very consistent with what we got before. Also checked my calculation up here while I was at it, and that's actually closer to 20. It's actually about 19.7. That made very little difference. The angle came out over 76.5 degrees. It's still rounded to 77. And I think I actually got that backwards. Anyhow, whether we use 21 or 19.7, the result came out rounded off to the nearest degree to 77 degrees, consistent with our preceding calculations. And you should find that somewhat enlightening, maybe even a little bit impressive. Impressive regarding the method, not my execution of it. A couple of things I'll draw your attention to. All our drawings of F12 and F13 have shown this angle pretty clearly being a little bit less than 90 degrees. So 77 degrees is pretty well consistent with the way everything has been sketched. The other thing regarding units, and let me just point out that I carried the units throughout all of these calculations, and it's, I think, an important habit to do so. When you stop using units, you stop thinking about what things mean, and you lose all kinds of consistency checks that can reveal errors in your procedure. So, newtons times newtons gave me newtons squared here, so that the F1.F2 was in newtons squared. The magnitudes are both in newtons, so I have newtons squared here, and as advertised, the cosine of theta comes out to be a pure number, as it must. And then we can take the inverse cosine of that pure number. If the units of this came out in newtons, it means that you did something wrong. You either used a wrong procedure or you just accidentally screwed up your unit calculation, something you should never do, something you should always be very careful with.